Hi everyone, welcome to G World of Academic Physics. Today we will discuss one more application of electric field, that is Gauss Law. What is the statement of the Gauss Law says? It is written like this, that E dot ds is equals to 1 by epsilon naught times the amount of charge enclosed. I just want to repeat the statement in a literature form, that the surface integration of electric field over any closed surface is equals to 1 by epsilon naught times the amount of charge enclosed within the Gaussian surfaces. One more time, the surface integration of electric field over any closed surface is equals to 1 by epsilon naught times the amount of charge enclosed within the Gaussian surface. Here the most important thing your student has to be mind in your mind, that E is the net electric field, is the net electric field of the system, and flux is due to the amount of charge enclosed within that Gaussian surface. E is the total electric field or the net electric field of the system, but we are always counting the flux is due to the amount of charge enclosed within the Gaussian surfaces. And second most important statement that we have to withdraw also in the sense that if the net flux of the system is 0, the net electric field of the system is not 0, but the net electric field of the system is 0, the net flux of the system is 0. The surface integration of electric field over any closed surface is equals to 1 by epsilon naught times the amount of charge enclosed within that Gaussian surface. This is the statement. And important thing is the net electric field of the system, but we are counting the flux only the charge enclosed within the Gaussian surface. How to prove this statement? Let's prove this statement. This is a charge q which is enclosed within a Gaussian sphere. I said the Gaussian sphere is like this, and the radius of this Gaussian sphere is r. This is a positive charge, so definitely the field lines are radially outward. So everywhere the field lines will be go like this. It will be go like this. Everywhere the field lines are radially outward. Let's consider a very elementary area is here. I will consider a very elementary section on the sphere. And I said the direction of the area vector is always perpendicular to the plane, but in case of a closed surface it is radially outward. So direction of the area vector, it is this directions. This is my area vector, and direction I am preferring as r cap. And due to positive charge, as the field lines also radially outward, so I will prefer this direction of the electric field also along the direction of the area vectors, because electric field lines exactly at this section the field lines will be go like this. So this is pretty clear. The electric field lines and the area vector are parallel to each other. If I will go my LHS part, this is nothing but E dot ds, and this is which integration? Surface integration over the closed path. What is the angle between E dot ds? I am considering the LHS part. The angle between E dot ds is 0 because area vector and electric field vector are both parallel to each other. So I will simply write E ds cos 0, because r cap and r cap product is giving rise to 1. So this is nothing but integration of E ds. And if I will make outside, this is my E, this is integration of ds. And we know this is a sphere. So what is the area of the sphere? Simply I can write 0 to 4 pi r square. So definitely we will get E into 4 pi r square. And this is a point charge, and due to point charge, what is the expression of electric field? The expression of electric field due to a point charge is kq upon r square into 4 pi r square. And what is the value of k? The value of k is 1 by 4 pi epsilon naught. I will simply substitute the value of k, that is 4 pi epsilon naught r square into 4 pi r square. If you observe carefully, the things have cancelled out, we will get that q upon epsilon naught. and this q is enclosed within this Gaussian surfaces. That's why it can be written as q enclosed upon epsilon naught. This is a very basic proof that a student has to be in the mind for the board papers. These questions can be asked for 2 to 3 marks. So one more time I want to repeat the statement that the surface integration of electric field over any closed surface is equals to 1 by epsilon naught times the amount of charge enclosed within the Gaussian surfaces. Here E is the net electric field and the flux is due to the amount of charge enclosed within the Gaussian surfaces. If I will go for the basic proof of this Gauss law, what I will consider? I consider a charge q which is enclosed within a Gaussian surface and the Gaussian sphere of radius r. I consider a very elementary section of area is here. The area vector is like this, because we know area vector is always perpendicular to the plane, but in case of a closed surface it is radially outward, perpendicular but outward rather than inward. So ds r vector, and electric field also for positive charge radially outward. In this small section the field lines are radially outward. So electric field vector and area vectors are parallel to each other. Due to that the angle is 0, and proceeding the similar fashion we know the expression of electric field due to a point charge is kq upon r square. Putting this area is a sphere, that's why I am putting this area of the sphere and going for the basic calculations will reach this thing that q enclosed upon epsilon naught. If I want to generalize the Gauss law, if I want little generalized way, if I want to explain this Gauss law, what I have considered, I consider any random closed Gaussian surface, and this is q1, this is q2, this is q3. Suppose q4 charge is outside. If I will go for my electric field, that is the total electric field where q1, q2, q3 and q4 all the charges have included, but the flux is only due to these 3 charges rather than this charge, because inward whatever the electric field lines have been entering, the same field lines are emitting out of the surface. So that's why inlet and outlet have cancelled to each other. That's why we are not considering the flux of this charge. If I will go for my basic way of Gauss law, I will write my Gauss law, that is nothing but E dot ds is nothing but q enclosed upon epsilon naught, and due to all charges I will write my all electric fields. Let's write the electric field. This is E. Due to charge 1 I will write that is E1 dot ds. This is q1 upon epsilon naught. This is first equations. Due to q2 I will write this is E2 dot ds. This is q2 upon epsilon naught. This is equation 2. Similarly, if I will write for the third charge, this is E3 dot ds. This is what? q3 upon epsilon naught, and E4 I will write E4 dot ds, but no charge have enclosed, that's why this is 0. Flux is 0, but electric field is not 0. This is very careful thing. If a flux is 0, net flux of the system is 0, that the net electric field of the system may or may not be 0. This is a very quoted statement a student has to be remember in the mind. If I will write my total electric field, this is nothing but E1 vector plus E2 vector plus E3 vector plus E4 vector dot ds, which is nothing but q1 plus q2 plus q3 plus 0 upon epsilon naught. So similar fashion, this is I will write the net electric field dot ds equals to the amount of charge enclosed, q enclosed upon epsilon naught. So student has to be pretty clear in the mind that if the net flux of the system is 0, the net electric field may or may not be 0, but the net electric field of the system is 0, the net flux of the system is 0. This is a pure indication that here E1, E2, E3, E4 exist, but the flux is 0. This E dot ds is nothing but that flux is 0, but net electric field may or may not be 0. So adding up all electric field, we are getting the net electric field of the system. This is a very generalized way a student has to be remember. Let's go to the application of the electric flux. I will go for a hollow non-conducting sphere. and we'll discuss about these are the board questions usually come for this Gauss law. So I will consider a hollow non-conducting sphere and the radius of the sphere is r. How many regions have exist here? One is region 1, second one is on the surface, this is second region, and third one is outside the region. The question will ask you find the electric field on the all the three regions, means E inside, E on the surface, another one is E outside. These are the questions that can be asked in a board papers. So let's discuss one by one. The first thing is, this is a hollow non-conducting sphere, so definitely charge is uniformly distributed over the surface of the sphere rather than inside. Hollow non-conducting sphere, hollow everything is lies on the surface, the Q charge is uniformly distributed all over the surface rather inside. If I will write for E inside, electric field inside, what is the expression? I will choose a point and that point must be enclosed by a Gaussian sphere. As I enclosed and I said the radius is r, but what the thing is happening, within this Gaussian sphere there is no charge has enclosed. If I will write my Gauss law, E dot ds equals to Q enclosed by epsilon naught, but charge enclosed in this section is 0, that's why the net electric field inside is 0, because Q enclosed is 0. I hope the scenario is clear, because charge is lies on the surface of the sphere, hollow sphere, rather than within this Gaussian surface. If I will go for the outside region, let's choose a point here and that point is enclosed. That point is enclosed within the Gaussian sphere. I will construct a Gaussian sphere. I am thinking for the outside region electric field. So I will now the radius of the Gaussian sphere is r. I will write my Gauss law. So I am looking for the outside point. So I will write my Gauss law, that is E dot ds equals to Q enclosed upon epsilon naught. What is the angle between E and ds? That is E and ds angle is always parallel to each other, because already in the previous proof we discussed this thing that E ds are mutually parallel to each other. So angle between them is 0, so definitely I can write as E ds, and this is Q enclosed upon epsilon naught. How much charge is enclosed? How much charge is enclosed within this Gaussian sphere? The Q amount of charge is enclosed, so that's why the Q upon epsilon naught. ds, this is usually student feel the difficulties that ds is whose area? That is the Gaussian. ds is what area? That is the Gaussian surface area. This is very important thing. ds is the Gaussian surface area. So I am writing the Gaussian surface area as 4 pi r square, because radius of the Gaussian sphere is r. So this is Q upon epsilon naught. So directly I can write Q upon 4 pi epsilon naught r square. This is kq upon r square. So a student has to be very clear, this is the expression like a point charge expressions, and this is pretty obvious. Suppose this is a sphere and the expression is coming like a point charge. If I look, suppose this point is here, this point I want to find my expression of electric field, it is coming like a point charge. If you little larger, this point is here, and little further larger, if I see very large distance, this sphere look like a point. If I will make my distance little larger, can I feel this sphere can be like a point? Yes, like a point charge, and this is the obvious that the expression will become like a point charge expression. One more time I want to explain these things. Suppose this is a sphere, I am looking this sphere to the outside point here, it is observable that look like a sphere. If I will increase my distance and move on and on, I can find a very largest distance, this behaves like a point charge. So this expression is obvious, it will be come out to be like this. And on the surface, we know that on the surface the small r, if I will draw my Gaussian surface exactly on the surface, I will get that small r is nothing but capital R. So on the surface small r is equals to capital R, so I will get the expression is kq upon r, capital R square. So it is pretty obvious. If I will draw my electric field versus R graph, This is my electric field, this is my R graph. If I'll plot the things, how many regions? 3 regions: inside, on the surface, outside. On the surface, small r is equals to capital R. We know that there is no electric field inside this region because no charge is enclosed within that Gaussian surfaces, so no expression of electric field. Exactly on the outside, on the surface, the expression is here, that is kq upon capital R square. After that, E is inversely proportional to R square, like a point charge expressions. So definitely it will be like this. Already in the point charge, how the graphs will become, we have already discussed these things. And where this electric field come to 0, at infinite this field comes to 0, because when R is infinitive, E is coming to 0. So definitely student usually do the mistake and connect like this. No, this will be go to Anant, and after infinitive this will come down to 0. I hope the expression is pretty clear. Let's go to the solid sphere. Non-conducting solid sphere. This is my solid sphere. Charge is uniformly distributed on the solid sphere. The radius is r. Having volume bound charge density is rho, and q charge is uniformly distributed all over this solid sphere, inside as well as on the surface also. And volume bound charge density is rho. This is volume bound charge density rho. Rho can be defined as charge per unit volume. Charge per unit volume. I hope these are the small things already we have discussed in the previous lectures. So how many regions again? The 3 regions: inside region, on the surface region, and third region is here. And that is also very obvious things. If I look hollow sphere or solid sphere outside, it like a point. Because if this point is here, I am observing from here. If I'll little further and further, if I'll move like this and I'll observe this hollow sphere or solid sphere outside, then it like a point charge. So it is obvious that the expression will come like a point charge. So this is for a hollow sphere or solid sphere, E outside, the expression is kq upon r square, small r square. This is because if I will draw one Gaussian surface here, I will draw the same pattern. I will draw the radius of the Gaussian surface is r, and I will write my Gauss law, that is E dot ds equals to q enclosed upon epsilon naught, and E ds angle is always parallel to each other. So E integration of ds, how much charge is enclosed within this Gaussian surface. This is the q amount of charge is enclosed within this Gaussian surface. So this is q upon epsilon naught. E ds is whose area? Gaussian surface area. The Gaussian surface radius is r, so definitely the area is 4 pi r square, and I will proceed in the similar fashion. I will get expression is q upon 4 pi epsilon naught r square, that is kq upon r square, like a point charge. This is pretty obvious. If a larger distance I will observe these things also, I will get these expressions. And on the surface that small r, on the surface this small r is equals to capital R. So definitely the expression on the surface is nothing but, this is surface, is nothing but kq upon capital R square, because small r equals to capital R exactly on the surface. Now little important is what, give the attention that inside region how much electric field. If you observe carefully, I am looking for this point, so I will enclose a Gaussian sphere, and the radius of the Gaussian sphere is r, and I will write my expression of electric field within this Gaussian sphere, how much charge is enclosed. So I will write first my Gauss law, that is E dot ds equals to q enclosed upon what? Epsilon naught. This is the basic Gauss law, and this is pretty obvious that E ds angle is always 0, so I will write my E integration of ds. Now it is very important that how much charge have enclosed within the Gaussian surface. If you observe very carefully, this is in bigger sphere, the charge is these things. Within this sphere how much charge? So we will use a technique. The technique is, that is charge per unit volume. This is 4 by 3 pi r cube. Charge per unit volume, this much of charge. Within this volume, how much of charge? Into that volume, 4 by 3 pi small r cube. Upon what? Epsilon naught. This is the concept student has to be found here, that this is charge, total charge enclosed within the solid sphere is q. I want charge enclosed within this sphere. How much charge is enclosed? So I will use charge per unit volume. Into that volume, this much of charge is enclosed within the Gaussian sphere. And this is whose area? Gaussian surface area. This is 4 pi r square. And this is 4 by 3 cancel pi. These are the things have been cancelled out. And if I proceed, I will get that q r q upon r q epsilon naught. And little cancel out this r square here r. I will get the expression E equals to 1 by 4 pi epsilon naught q r upon capital R q. This can be written as k q r upon r q. So E is directly proportional to r. This is one information we observed here, and here we already have E is inversely proportional to r square. This is very important. A student has to be in the mind outside what is the expression of electric field, that is kqr upon rq. Because how these expressions came out? Because charge enclosed we want within this region. How much charge is enclosed within this region is nothing but charge per unit volume. In a unit volume, this much amount of charge. In that volume, how much amount of charge? I just simply multiply that volume. I will get the expressions kqr upon rq. If I will go for my in term of volume bound charge density, sometimes this kind of also things can be asked, that E into 4 pi r square in term of volume bound charge density. If I want to explain these things little carefully, here this is rho, because this whole thing charge per unit volume can be written as, look at these things, charge per unit volume can be written as rho, and this is nothing but 4 by 3 pi r cube upon epsilon naught. So what are the factors have been cancelled? 4 cancel, pi also cancel, and 1 r is cancelled like this. So expression is coming rho r upon 3 epsilon naught. So outside student has to be remembered three things, that inside it is kqr upon rq in term of volume bound charge density, that is rho r upon 3 epsilon naught. If I will plot my graphs E versus R in all the three regions, this is my electric field, this is the R, and I want to plot the graphs. How many regions? One is inside on the surface, outside. Inside on the surface, small r equals to capital R, and we know that inside it is varies directly proportional to R. It means a linear graph nature will become, because E is directly proportional to R. So definitely this is a linear graph is coming, that E is directly proportional to R. After that, at this point the expression is kq upon capital R square. After that it will be go like this, and here where it will come to 0? At infinite it will come to 0. In case of hollow, that was empty, there will be no electric field inside that region. But in case of a solid, the expression is what? kqr upon rq or rho r upon 3 epsilon naught. These are very standardized result a student has to be remember in the mind. Let's go for more applications, that we will go for solid cylinder. This is solid cylinder, and this is non-conducting solid cylinder we are looking for. Non-conducting solid cylinder. So I will construct a solid cylinder, and the radius of the cylinder is r, and having volume bound charge density is rho. So how many regions? There are three regions. One is inside region, another is on the surface region, another one is outside regions. So first thing we'll think as per the convenient way. Let's think about it, how the things have been going on. And total charge is q, that q amount of charge is uniformly distributed, having volume bound charge density is rho, and radius of the cylinder is r. Let's, how many regions I will go for? 1, 2, 3 regions. Let's draw one by one. Outside region, if I are considering, I will draw a Gaussian cylinder. This is my Gaussian cylinder which is enclosed, and I will write the radius of the Gaussian cylinder as r, and I will write my basic Gauss law. What is my basic Gauss law says? That is E dot dr is nothing but q enclosed upon epsilon naught. So this is my E, because already the angle between E and dr is always is what it is, you can consider to be parallel to each other. And this is little carefully you have to be think this Gaussian, if you are thinking for a cylinder, it has two surfaces, one is curved surfaces, another one is flat surfaces. Flat surfaces, the area vectors have been like this and electric field lines have been like this. So definitely for the flat surfaces for the cylinder, the electric field lines have been like this, because it will be go like here, here like this, it will be go like this. So definitely it is pretty clear that if I will consider a cylinder, I am talking the top view of the cylinder, the field lines will be like this. So definitely it will it is perpendicular to the area vector. So for the flat surfaces, because this E dot dr having two surfaces, one is E dot dr for flat plus E dot dr curve, and is nothing but q enclosed upon epsilon naught. This is a pretty theory that you have to be in your mind. Due to flat surfaces 0, because E and dr are mutually perpendicular to each other, the Gaussian, the area vector and electric field vector are mutually perpendicular. So we are not looking for these flat surfaces, because area is like this, electric field lines like this, angle between them is 90 degree. So you are only looking for which surfaces? Only curved surfaces. And we know that area vector and electric field vectors are parallel each other, because I will consider one element is here, area vector also like this, electric field also like this. So definitely they are parallel to each other. So I will make E like this, integration of ds. This is little carefully I mistaken this Gauss law, this is ds. So this is ds. This is a little wording errors you can say. Area vector is in this case it will be 0, this is E ds, and how much charge is enclosed, that is within this Gaussian surface this q charge is enclosed, so q upon epsilon naught. ds is whose area? Gaussian surface area. ds is what area? Gaussian surface area. So it is pretty clear that I will go for the Gaussian surface area. What is the area of the cylinder? The area of the cylinder is nothing but 2 pi r, the radius of the cylinder, this is Gaussian, into length of the cylinder. If I will consider the length of the cylinder is suppose L, is nothing but q upon epsilon naught. The expression is coming up what? Q upon 2 pi r L epsilon naught. This is in outside region, the expression is coming like this. I hope this scenario is pretty clear to everyone, that for the flat surface no electric field, only we are looking for the curved surfaces, and curved surfaces E and ds are mutually parallel to each other. We will only look for ds is whose area? Gaussian surface area. And in this case, what is the area of the Gaussian surface? The cylinder area. What is the area of the cylinder? It is pretty easy that one can write the 2 pi r, because radius of the Gaussian surface is r and length is L. So that's L. This is the expressions. And on the surface, this small r equals to what? Capital R. So on the surface, this small r, on surface, this small r equals to capital R. So this is on the surface, one student can directly put that 2 pi capital R L epsilon naught. This is not a big deal at all, because on the surface, this small r equals to capital R. This is very important, that inside the region, what is the expression of electric field? Inside region, if I look for the inside region, I will construct a Gaussian sphere like this. The radius of the Gaussian sphere is, I will consider the small r, because inside I want to draw my electric field. So this is my Gaussian sphere, the radius is here, and the original sphere is capital R, and charge is enclosed q, and having volume bound charge density is rho. So this is very pretty, that we will again move like this, E dot ds equals to q enclosed upon epsilon naught. Again E dot ds for due to how many surfaces? Two surfaces, one is curved and flat. For the flat surfaces, already that electric field and area vector are mutually perpendicular, so no expressions, only we will go for which surfaces? Flat surfaces. So flat surfaces, E ds parallel to each other, E is outside, ds, and this is how much charge is enclosed. The similar concept I will use, charge per unit volume. What is the volume of the cylinder? That is pi r square L into this volume. this is pi r square L upon what? Epsilon naught. ds is whose area? Gaussian surface area. So I will simply write the Gaussian surface, that is 2 pi RL. And what are the things have been cancelled out? This L and this L cancel, pi cancel. So q r square epsilon naught. These the things have been coming out. And little adjustment if I will do, E equals to q, this r also 1 r cancel. So q upon 2 pi epsilon naught r square, this is small r is coming like this. This is inside region, the expression of the electric field. In term of volume bound charge density, if I look here, so this is my E, this is 2 pi RL because Gaussian surface area, and this can be written as rho because charge per unit volume, that can be written as rho into what? Pi r square L upon epsilon naught. What are the things have been cancelled out? Pi cancel out here, 1 r cancel out, L also cancel out, and the expression is coming rho r upon 2 epsilon naught. This is inside, in term of rho, in term of charge q, this is the expression is coming out. This is pretty clear, very similar fashion if you look at the solid sphere inside, that is rho r upon 3 epsilon naught. But in case of a solid cylinder, that is rho r upon 2 epsilon naught. These are the small things the student has to be in the mind for the competitive perspectives, and these are the basic things, that basic Gauss law we are looking for. And one more application I want to draw here. This is non-conducting thick sheet. This is little important, I want to make it for the student perspective. This is a non-conducting thick sheet. How the thick sheet will look like? This is a non-conducting thick sheet. As a thick sheet will be look like this. If I will construct this sheet, it will be look definitely like this, and you will be connect like this. This section also connect like this. This is, you can say this is your thick sheet looks like this. So I am considering only these sections. So it will be thick sections I am considering. You can say your book or notebook like something. And this thick section, we are looking for this thick section. I said the volume bound charge density is rho. And the question will ask you, what is the expression of electric field outside and inside of this thick sheet, non-conducting thick sheet? So exactly I will divide like this, and I will say the width is, total width is d. So exactly half of the width is obvious, this is d by 2, this is d by 2. If let me redraw these things, only this section I want to draw here. So I am considering this section here. This is my thick sheet sections, and this is the total distance is d, I said, and here it is d by 2, and here it is d by 2. So how many regions I am looking for? There will be two regions. One is inside, another one is outside. Let me think about the inside region. I want to, if this kind of sheets approach have been there, we are looking for what? We are looking for a Gaussian cylinder. So I will construct a Gaussian cylinder is here. This is little important, a student has to think about it. That we are considering a very small section of the sheet whose area is A. I will say this distance is x, and this distance also x, and area is A. This area also A. So if I will write my Gauss law for this inside region of the thick sheet, I will write E dot ds equals to what? Q enclosed upon epsilon naught. This is my Gauss law. E ds, how many surfaces? Flat and curve. Flat and curve. This is carefully E ds due to flat, plus this is E ds due to curve is nothing but what? Q enclosed upon epsilon naught. If you observe very carefully, this is my Gaussian sphere, a Gaussian cylinder, and the area vector is outward, electric field also outward. Here area vector is like this, and electric fields have been also like this. In this case, area vector is like this, but field lines have been like this. So definitely they are mutually perpendicular. So for the curved surfaces, this thing is 0. So we are only looking for the flat surfaces. And how many areas? One is EA, another one is EA. So EA plus EA, because angle is 0 degree, E dot A, and it is parallel to each other. So 2EA equals to charge enclosed. In term of rho, if I want to write, rho into V, volume. Volume is how much? Length into area. Length is what? 2x into area is what? A upon epsilon, because total length is what? 2x. So that is 2EA equals to what? Rho 2x A upon epsilon. If I will cancel out this thing, 2 have cancel, A cancel. So expression is coming rho x upon epsilon. So inside a thick sheet, non-conducting thick sheet, what is the expression of electric field? The expression of electric field is rho x upon epsilon naught. If I will go for the outside region, look at the outside region. If I will think like this, this is my outside region. Here I am looking for. If I look outside region, so the similar fashion I will write my flat and curve. Which thing have cancelled out? Only flat section will be exist. So this is E dot ds equals to q enclosed upon epsilon naught. So write my EA, this is EA plus EA. This is obvious because two sections, that is EA plus EA. And I will write charge enclosed in term of rho. Rho is nothing in rho into V, volume. What is volume? Total length into area. So it is nothing but D into A upon what? Epsilon naught. So this is the expression have been coming as 2EA equals to rho dA upon epsilon naught. Cancel out the 2, sorry, no, 2 is not cancel, A cancel, and the expression is coming outside is nothing but rho D upon 2 epsilon naught. It is very clear, inside it is directly proportional to x, but when it reach to the surface or outside, it is rho d upon 2 epsilon naught. This is a very important thing the student has to be clear, that outside the electric field is constant because this width length is constant. That's why the expression of electric field rho d upon 2 epsilon naught is constant, but inside it is varies with x. If I will plot my graph, this is my width. I want to plot the graph versus E versus x graph because the distances have been moving. See carefully up to d by 2 because x increases. So this sections up to d by 2 it is linearly vary because E is directly proportional to x. So E is directly proportional to x. After that it is constant. So this duri is what? D by 2. It will be varies like this. After that it is coming what? Constant. In the similar fashion, in this section, it is also up to d by 2, it is constant, linearly vary, and after that it is constant. This is the graph nature that student has to be in the mind in case of a thick sheet, non-conducting sheet. Let me explain one more time. This is a thick sheet. The width of the sheet is T, having volume bound charge density is what? Rho. What I did here, I will go for the first inside. I will consider a Gaussian cylinder is here. Here student has to think why we are consider a Gaussian cylinder, because this is an infinite thick sheet. You can consider infinite thin sheet. We are considering a Gaussian cylinder is here. Here one question also I will left for the readers. Those have been looking also viewers, that why not I will consider a cube or something to enclose this kind of things. Why is it easier to prefer this Gaussian cylinder? I hope those have been watching, they can also put in the comment section that why not I will consider cube or any other surfaces rather than this cylinder. This is flat, this is curved. For the curved surfaces things have been coming 0, and I will write for the flat surfaces electric field and volume bound charge density rho into V, length into area can giving rise to what? Volume. And I will go for the expression, I am getting this result. Similar fashion I will go for the expression for the outside. outside also I will, this is outside point, I will draw one Gaussian cylinder like this. This is my Gaussian cylinder like this. But up to what length I can proceed, this is the maximum length I can prefer. So this is the maximum length, so that's why length into area, that is giving rise to volume. And it is pretty obvious that it is varies linearly up to x. When it reach on the surface or outside, it is remain constant. Similarly below also like this, and it is constant. That's why the graph nature will be coming like this, and this is obvious. I hope the scenario is pretty clear. Due to time constraint, we have to end up this video. In the next sessions, I will bring some more application of the Gauss law for the student benefits. Thank you everyone. I hope that you guys will subscribe and follow these things. Thank you everyone. Thank you for your watching.